Welcome to section 3.2. This section is a continuation and a build upon, I guess, of our last section in which we learned about symbolic logic, at least some of the main definitions that are going to be there. And it extends us into something called truth tables. So truth tables are formed by compound statements. If you remember, a compound statement puts together two statements, typically with the words and, or, and they even consider not to be a compound statement. Compound statement is one that we really have to think about. Okay, what's the effect if I know this and I know that? And how do those work together? And so one great way that that takes place is through this concept of truth tables. So the purpose of this video is to share with you all the truth tables that are there for and, or, and not. This will mirror what's happening in the 3.2 homework. And then we'll also establish truth tables for things that are a little bit more complex of a compound statement. But let's start with the truth table for P and Q. So what P and Q represent are two different statements. So P could be, I'm going to pass the class. Q could be, I'm going to get an A. And so for P and Q to happen, both you would need to pass the class and you'd have to get an A in order for the statement to be true. But P and Q just represent any old statement. And so that's what's really nice about symbolic logic is you can take these statements that are being made, translate them into letters so that there's no emotional attachment to them. So here's the truth table for P and Q. So remember the symbol for and. I'll remind you that right here. And has this symbol of an upward facing arrow. That's the and symbol. So you'll see it just like that. So the way a truth table works is you have P and Q there. And you also have the compound statement P and Q. And what's going to happen here, and you can see this same truth table in the book or if you look at the videos, but you're going to go through all the possibilities. P could be true and Q could be true, right? So if P is true and also Q is true, what about the compound statement P and Q? Well, that would also have to be true because an and statement, if you don't know that already, it needs both to be true in order to work. So think about this from our statistics standpoint. If we were wanting a student and somebody with black hair, so if I went out into the city of Folsom and I wanted to get an FLC student and somebody with black hair, I would not be successful if I grabbed a person that had brown hair that didn't go to FLC. And likewise, I wouldn't be successful if I grabbed somebody from FLC and they didn't have brown hair. So they both need to be true in order to work. So if I consider P to be my, if I let P be my FLC student and Q to be brown hair. If I go out and I find somebody who, true, they are an FLC student, and true, they have brown hair, then P and Q would also be true. If I go and I find somebody that's an FLC student, but they do not have brown hair, they fail at that brown hair, then I do not have somebody who is an FLC student and has brown hair, and I fail at that as well. If I fail at the first condition, but the second condition is true, then we overall fail in that regard. And then if I fail and fail, then obviously we fail. So thinking about this for my FLC brown-haired student, I would like to get somebody that is an FLC student and has brown hair. So if I go from the bottom, what this false right here means is that they're not an FLC student. And this false right here means they don't have brown hair. So obviously if they fail in both categories, then we fail overall to have a person that's an FLC student and brown hair. Now if I go up one level and we look at this one right here, then they're a not FLC student, but if I go up one level here, then they do have brown hair. Well, even though they have brown hair, if they're not an FLC student, then I do not have somebody at the same time who's an FLC student and has brown hair. And so it's very much connected to the decisions we were making before with overlap and mutually exclusive in that regard. So you do have some frame of reference for this as we go forward. But that's the truth table for and, regardless of my brown-haired example, right? So with an and, they both need to be true in order for the overall condition to be true. If any one of them is false, then the overall condition is false. So I'll write that out. If any one statement is false, then P and Q is automatically false. The only way P and Q can be true is if they're both true. Well, that's not as the same if we go to the or statement. So remember what or looked like. The probability, wrong section. P or Q, right? So that's P and Q. And again, the truth table would go through the options for P. P could be true. P could also be false. And at the same time, Q could be true or Q could be false. Q could be true or Q could be false, right? And you get this same feeling every time. So you just kind of range through, hey, what do those pairs look like? Now you can write these truth tables down and bring them with you on the exam if you'd like, but I think you'll memorize them. Now, or is quite different. Or is saying, hey, I don't care if you have the first condition met or the second. As long as you have a condition met, we will accept you. So if it was selecting a person from Folsom and getting somebody that's an FLC student or somebody with brown hair, then if I go and grab somebody and find out that they are an FLC student, so this first category, and they do have brown hair, then I've met the condition then it's true, right? So as long as when they're both are true, then the overall condition is true. So let's go to this next one down here. So how about if the person that we select is an FLC student but has hair color different than brown? So the person I select in Folsom is an FLC student. They tell me that right away. Well, then they've also met my condition because this says or. So I don't care if they meet the first condition or the second. As long as they meet one, we're good. So when that person tells me they're an FLC student, even though they have blonde hair, I have found somebody that's either an FLC student or has brown hair. If I go to this next one and they're not an FLCD student, but they do have brown hair, well, I still have met the brown hair criteria. And the only way for us to have a false reading is if both are false. And so I hope my hair color and FLC student example helps to talk about this a little bit and help you understand it a little bit better. But essentially what we're finding here under the or is as long as one of the conditions is true, then P or Q is true. The only way, I'm going to state this in another way, the only way for P and Q to be false is if both P and Q are false, right? If neither condition is met. And so we have that or probability, or not probability, that or statement. It does have a very much a relationship with probability. Then the last one is not P. And so when we talk about not P, remember what that symbol looks like, because we start to use a symbol. that little wavy line, and a P. So here we only have one statement, and so that one statement, P, could either be true or false. And the not P then is false and true. It's the opposite. I think that one goes without saying. Right? We understand that one very intrinsically. But they do make us state it out and have us look at that. So those are the three main truth tables that are going to be used in this section. And what they'll do is they'll have you put together ones and create new ones based upon information. So let me give you an example. So as I turn to the homework examples that are here, and just the ones that are in the book, they're going to have you consider new statements. And those new statements are something like this. This is something I saw in the book. So this is your first example on this video. Example 1. Construct the truth table for, and here's what's written. Not P and Q, or not P. And again, the value of symbolic logic is it helps us to evaluate some pretty complex statements and be able just through truth tables to know the truth of them. And so I actually copied that down wrong from what's written there. So I want to make sure I'm doing the exact problem. And so they have a not Q here. So not P and Q, or not Q. And so we want to construct the truth table. So the truth table, as you look across here, there's really just two statements. There's P and Q. And so we start there and we do our true, true, false, false, and then true, false, true, false, getting every combination of what P and Q could be. Make that look like a false. And we're going to come, and my suggestion for this, when you have this, is realize that this extremely compound, this more complex one has, this more complex compound statement has two parts. It has that part right there, the yellow part. And let me back up off of that. Let's see if I can get that to be a little bit nicer. We have, oh, that's going to gray it out. So let me back up over that. And then I'll just try to be a little bit more direct here. I got this statement right here in yellow. And then I also have this blue not Q. It's really made up of just two things, but I got to get those individual pieces. So the next thing I'm going to do, keeping the color coding, is I'm going to find P and Q. So hopefully that yellow is showing up for you. And so actually, I'm going to even back up from there, right? Because I just realized that it wasn't just P and Q. It was not P and Q. So I'm going to come back to my black pen, and I'm going to create a not P row. So if it's not P, then I'm just looking at P, and I'll have false, false, true, true. And so we didn't necessarily have to put out what P and Q were initially, but it does help. Let me make these lines a little bit longer here, because what we're going to write in this next one is the yellow one. So we look at our complex statement, which is a complex compound statement, and we look at the two pieces, and we realize, okay, I got to do not, let me back up there, I didn't grab the right style of pen. Apologize. We're going to do not P and Q. So remember about the and. In the and, if I come back up here with the and, they both need to be true in order for it to work, or in order for it to be true. So only times an and statement is true is if they're both true. So realize what I'm putting together, not P and Q. So this one's going to be false. And the reason why it's false is they're not both true. The second one's going to be false, but the third one's going to be true. And the last one's going to be false. So I'm going to get false, false, true, false. Again, an and statement will only be true as if they're both true. Then we have this other statement, right? And that is the not Q. So I'm going to make sure I do my not Q next and get those together. So Q was true, but now it's false. And then Q was false, but now it's true. Q is true, so not Q is false. Q is false, so not Q is true. And that's needed so that I can compare these two statements at the end, right? And so we get this nice little buildup. So I do think it's necessary to put the P's and Q's. They typically will show them that the more I think about it, the better that is. And so remember what we have here. In fact, I need to be a little bit more careful and realize that I'm going to need a bunch more room to describe what this is. I don't need the room for the true falses down here, but I need the room for this statement of not P and Q. So I'll put it in blue. So now we have not P and Q or not Q. Well, those are just these last two ones right here. So we're going to come up here and remind ourselves that, oh, as long as one of them is true in an or statement, the whole thing's true. So as I look across this, the first one has to be false because both are false, but the other ones are all true because at least one of the elements are true. And so this helps me establish, the truth table for, whoa, if I have something really complex and the two things are true, then the not P and Q or not Q would be false. If they're both false, it's going to be true. If one of them is false, then it's going to be true. And I can understand a little bit more about the logic that's involved there. Oh, I'm making a true statement here. And so I realize this is how people talk a little bit. They say, hey, not this, but this, and not this and this. And so we need to be careful that we judge things for the way they are. So you want to look at this as more of an exercise to get used to the and requiring both to be true and the or requiring only that they are all false in order to be false. And so we get some good practice there. Now, some other things that are brought up in this section that you'll be asked questions about is sometimes you'll have logical statements that have, and let me go back to the black color, they have P, Q, W, X, right? They have a bunch of statements. And so if you look at the number of rows in our truth table, there are 4 rows in all of our truth tables so far. And that's because we've only had 2 ones. If we expand it and have 3 variables, then what they found is that you will have 2 to the n rows when you have n statements. So for example, if you saw P and not Q, or not W or Q, well, you may have a lot of columns in order to figure that out, but in terms of number of rows, the different statements are P, Q, and W. Those are the 3 statements that are involved. So we would have 2 to the 3rd rows needed, or a total of 8 rows needed, right? That's what 2 to the 3rd is. And some of the questions are just like, hey, how many rows do I need? So you may have to grab a calculator. Maybe there'll be 4 or 5 variables. And so maybe you don't know what 2 to the 5th is. Not a problem. We can just run it. And so, that's how you can name how many rows. And you'll see us do that problem in the homework. The last thing that they talk about in the section here is, this is still 3.2, is that when you take, they give it a name, they call it De Morgan's Law. And De Morgan's Law is about taking the negative of a compound statement. And what it says, what De Morgan's Law says specifically, is that not P or Q is equivalent to, they'll use 3 equal signs. So 3 equal signs means it goes backwards and forwards. It's totally equivalent to not P. So this is not P or Q. I might have misspoken there. Not P or Q is not P and not Q. And not P and Q is equivalent to not P or not Q. So if you don't have both, then one of them is failing. So let me see if I can help this make sense. So what you see is that the not is being distributed to both, and then you get the exact opposite arrow direction, which means you're switching from an and or. So remember, this is an or, this is an and, this is an and this is an or. So let me give you an example. If I said, hey, I want the opposite, I want the negation of somebody who graduates or has a GPA greater than 3.5. So if I want the opposite of somebody who graduates or has a GPA of 3.5, then the only way for that to fail is if the person does not graduate and the person does not have a GPA greater than 3.5. So think about somebody who graduates or has a GPA of 3.5 or higher, right? Or a GPA higher than 3.5. If they have a GPA higher than 3.5 and they don't graduate, that's still a success for us, right? The or says, I don't care what category. So the only way for this to be false is if they're both false at the same time. That's a good way to look at it, I think. If it's the negation of the person graduates and they have a GPA greater than 3.5, then the only way that doesn't happen is if the person doesn't graduate or if the person does not have a GPA greater than 3.5. If the person does not have a GPA greater than 3.5, we fail. If the person doesn't graduate, we fail. So if either of these conditions isn't met, then the and condition isn't met. And so you'll apply De Morgan's law, and essentially you're distributing the negation and then changing the symbol. So we'll look to the homework to see what examples we have. The big thing is that we're creating these truth tables. And if it's an and truth table, then the only way for an and statement to be true is if they're both true. The only way for an or statement to be false is if they're both false. Every other situation results in true. Not P, I think we understand pretty well. And then we're going to have to construct these truth tables by utilizing those ones. So I think it's going to be a good experience as you go through this homework, but let me know. You can come to the Zoom sessions or you can reach out to me via email. Either way, I'm happy to help. Thanks for watching this